A very good evening to you all, and welcome to today's CCNA1 networking training for instructors. Today we'll be looking at Module 8. If you're joining us for the first time, you may need to check the YouTube channel, click subscribe, and watch the other previous modules 1 to 7. But if you have been with us all through, it will be good that we will continue. If you have a question, always drop it in the comment section in case I'm not able to answer the question live direct. Today, we'll be looking at the topic network layer. The network layer is the layer 3 of the OSI model that we are looking at. We have looked at the physical layer, which is the layer 1, and it is basically responsible for how network media is connected to the end device, especially how the data is transformed into the network media. And we understand that in the physical layer, the PDU is known as bits because that is the final layer where the data will be converted into machine learning, machine language. Okay, so we are looking at bits. In the layer 2 is called the data link layer, and we saw that the data link layer has two sub-layers. It has the media access control layer, which relates with the physical layer, and it has the logical link control layer, which relates with the network layer and the upper layers. And the data link layer, as we have seen, it operates at layer 2 of the OSI model. At the same time, it also functions based on the device network switch. So the network switch is the major device at the layer, at the data link. The PDU is known as the frame in the data link layer. Okay. Here, we're going to be looking at the network layer. Now, in the data link layer, we saw it has its own header and it has its own trailer. The header, we said, contains most of the information that are required by the frame, to include the source MAC address, the destination MAC address, the start bit, the stop bit, and things like that. The trailer contains basically the error checking mechanism. Now, at the network layer that we're going to be dealing with, we're going to be dealing with the layer 3 of the OSI model. And in this layer 3 of this OSI model, we understand that we're going to be looking at the device router. There's the router, and then there's a layer 3 router. Okay. Now, we're going to be looking at the characteristics of the network layer. We'll be looking at the IPv4 packet. We'll be looking at the IP. Please, Uju Sunday, can you please stop what you're doing? Thank you. We're going to be looking at the IPv6 packet. We're going to also be looking at how a host routes, and then we're going to be looking at the routing table. If time permits us, we may look at module 9, okay? But if time does not permit us, we'll just stop at module 8, which is the network layer. Now, let's look at network layer characteristics. The network layer provides services to allow end devices to exchange data, okay? Like we can see, it is operating at the layer 3 of the OSI model. And it runs basically two protocols, IPv4 and IPv6. There are other protocols, but majorly is these two, IPv4 and version 6. The network layer performs 4 basic operations. Number 1, it does addressing of end devices. Okay. Then it does encapsulation, it does routing, and then it does decapsulation. So between the sender and the receiver, there is addressing. So both sender and receiver requires an address, and that address is the IP version, is the logical IP address. Okay, then it has the encapsulation, where it encapsulates data that is coming from the upper layers. All right. It also does routing, which does the act of determining the best path to forward the packet. Because once the traffic comes to the router now connects to multiple other routers in the internet, and then determines which one is the shortest, safest, reliable path in order to forward this packet so that it can reach its own destination. And then when it reaches its destination, it finally does what they call the decapsulation. Now, under IP encapsulation, IP encapsulates the transport layer segment. You see, from the upper layers, we have the data that comes in this form. And this data contains all the other information above the transport layer, which is the session, presentation, and application layer. Okay. And then the transport layer will then add its own header information, which is called a segment. Once it adds the segment, there are certain details in the segment we will look at in our class when we come to talk about the transport layer. By the time it gets to the network layer, you see this entire segment like this is encapsulated into this data. So it comes in form of like data in the network layer. So it is the network layer, after encapsulating it, it will now add its own IP header, which we're going to also look at today. Okay, so the IP can either be IP version 4 or IP version 6. Okay, and then the IP packet will be examined by all the layer 3 devices as it actually moves or traverses through the internet. Okay, so the IP addressing does not change from source to destination. In the last class, we understand that in the layer 2, which is the data link layer, the MAC addresses changes. It changes because it traverses through different devices. So the MAC addresses of each of those devices changes. But for the IP address, the IP address does not change. The same IP address that is the source or destination continues to roll until it gets to its destination. Now, some of the characteristics of an IP is that it is connectionless oriented. Connectionless oriented means that it does not need to establish the end-to-end before it begins to transmit data. That is connectionless. For instance, you see, let's say this is Victor here. All right. Victor wants to make a call to Esther. Victor wants to make a call to Esther. And if Victor picks his phone, and then makes a call to Esther, her phone will begin to ring. Once her phone is ringing and she has not yet answered the call, Victor cannot begin to transmit. He cannot begin to give his information to Esther. Until Esther answers the phone and says hello, then there would be communication. Now, this kind of setup is called connection-oriented method. Connection-oriented means that the source, the sender and the receiver, the source and the destination have to be in synchrony before transmission of data begin. But in connectionless oriented is the other way around. Okay, let's say this is Peter. This is Peter. Peter wants to send an SMS. He wants to send us an SMS to Rosaline. All right. He wants to send an SMS to Rosaline. Now, from his own phone, he can send an SMS to Rosaline even if her phone is switched off. The SMS will send. She will receive it when the phone is on. Or probably even if the phone is on and is not actually with her, the SMS will be delivered, or you will send an email, the email will actually be delivered. Now, this is called connectionless, which means that the device, the two devices do not necessarily need to be in synchrony, actively synchrony before they send a message. So that's connectionless. So we're saying IP is connectionless oriented. IP also has what we call best effort. Best effort simply means that it's going to be, there's no one particular way that is going to use to say, I'm sending my data. It's going to send in all different ways, but it will put in the best way to get the message delivered. And then media independent does not mean that IP must depend on wireless or fiber optic or copper cable. No, irrespective of the media, the message goes. So this is the details for connectionless. We said it does not establish a connection with the destination before sending the packet, and there is no control of information needed actually to synchronize or acknowledgement or something like that. Okay, the destination will receive the packet when it arrives, but no pre-notification are sent by the IP. So if there's a need for connection-oriented traffic, then another protocol will handle it typically. So that is it. When we say best effort, we're saying that the IP will not generate delivery of the packet. All right, the message comes to this router. This router now can decide which way to send the packet. It can decide to send it here. So packets are routed through the network very, very quickly. So some of the packets may actually be lost in course of the transmission. And if that is the case, that may reduce the overhead, or that may require a resend of that particular packet. So because it's best effort, it does not expect acknowledgement and things like that. And it does not know if the other device is operational or is receiving the packet or no. As far as it's concerned, it is just sending the message. It's just sending the message. And when we say it's media independent, we say that it cannot manage or fix undelivered corrupt packets, because IP cannot retransmit error after an error has occurred. All right. If IP cannot regain out of sequence packets, and IP must rely on other protocols for these functions to actually work. And in that same concept, we're saying that it does not concern itself with the type of frame required at the data link layer or the media type at the physical layer. It can be sent over any media type. Just excuse me a second from there. So we're saying that the IP is also media independent. So fragmentation is when layer 3 splits the IPv4 packets into smaller units. Fragmenting causes latency. And when you say latency, you're talking about how slow or fast the network is. But IPv6 does not actually fragment its packets, right? So let's look at the IPv4 packet. In the IPv4 packet header, it is the primary communication protocol for the network layer. And the network layer has many purposes. One, it ensures that the packet is sent in the correct direction to the destination, because you know that the traffic will go into different routers. It moves from one router to the other, one router to the other, and things like that. And that helps it. Then it also contains information about the network layer processing in various fields, all right? So it ensures that. It also ensures that the information in the header is used by all the layer 3 devices that handle the packets. Because as the packet moves from router to router, as it moves from router to router, there is encapsulation, decapsulation, and so on and so forth. And so the IP header ensures that. So what is actually contained in this IP header? Okay. very, very important is the source IP address and the destination IP address. And remember, we said that from the time the message is generated to the point that the message gets to its destination, the IP address, the destination IP address, and the source does not change. Okay, that is found in the header. Another thing found in the header is the version, where you talk about whether it's an IP version 4 or is an IP version 6 and things like that. Another thing is like the size of the header and the size of the packet is also found in the header. That is the total length is contained in it. It also have what we call the header checksum, where it uses to make corrections where there are errors and things like that. Okay. Then it contains the protocol, which is an IP protocol. It contains what we call the time to leave. The time to leave is let me share my screen on that so that you'll see. Where is this? All right. When you are talking about time to leave, if I run a ping on my system now, let's say ping Google.com, okay, you'll see that I'm getting a reply. But check what I'm seeing. You see this TTL. This TTL is time to leave. Now, what is this time to leave that you see here? The time to leave is the time allotted for this particular what do they call it now? For this particular packet to travel to the destination and come back and report. So it is saying that if in the course of the journey something happens on the journey, maybe there's congestion or maybe there's one of the router is not reachable or something, and the time expires because the time to leave will be decrementing until it gets down to 0. If the time to leave expires, that particular packet will be dropped. That's where sometimes you see a message called request timed out. Okay, you see something like request time out, something like unreachable. Unreachable, actually, the time to leave has gone to test and come back. But request timeout, the time that is being given to it is expired. Okay, so that the version talks about which version, whether an IP version 4 or an IP version 6. All right, we said the service actually talks about the different services that the differentiated services talks about like the quality of service that is being applied. The header checksum detects for corruption or errors, and then time to leave, and then protocol, source, and destination IP addresses. These are very, very important information that are found in the IP version 4 header. Now, let's compare it with the IP version 6 header. First of all, the IP version 4 header had IP version 4 address has 3 major limitations. Number 1 is that the address is depleting. That means it's finishing. We have basically run out of IP version 4. It's basically finishing in the world because it is a 32-bit binary digit. All right. So the number of devices, especially with the advent of Internet of Things, that is actually running out IP version 4. Okay. Then we have lack of end-to-end connectivity. Lack of end-to-end connectivity is there because in IP version 4, we're going to see very soon, we have what we call private IP addresses, and then we have what we call public IP addresses. So the private IP addresses are not routable over the internet, but the public IP addresses are routable over the internet. And so because of that, if I have a PC here in Lagos, for instance, and then I want to check maybe a server in Jos to see whether I can reach the device direct based on the IP addresses. I will not be able to do that because maybe this guy in the local network is giving a private IP address. But because there is a router here and I go to the internet, the ISP will give me a public IP. All right. So if me in my local area network in Lagos, I'm using a private. So I'm using a private, there's a private here, then in between the internet here is a public. So there is no end-to-end connectivity. Another thing that happens because of that is what we call NAT, Network Address Translation. It's actually a temporary solution that helps to ensure the maximization of public IPs. So what NAT does is that this guy in Lagos is using a private IP address. When the traffic gets to this router, then there will be NATing. NATing simply means that it will keep its own private IP address and pick the public IP address that is provided by the service provider. And because public IP address is routable over the internet, that IP address can go through the internet and go through the internet. By the time it gets to the destination router here, then there will also be another routing process, NATing process here to come inside here. All right. So if this guy wants to go private, there's a NATing going on here and things like that. So that is basically the concept of NATing. So IP version 6 was developed by the Internet Engineering Task Force to actually overcome the limitations that IP version 4 actually has. And so because of that, IP version 6 has improved on the limitations of IP version 4. What are those improvements? Remember, we said the IP version 4 is depleting, but in IP version 6, it has created more spaces because you see, IP version 4 is 32 bits, but IP version 6 is about 128 bits. 128 bits. So, for instance, now, if we're saying that IP version 4 is 32 bits, we're talking about billions of IP addresses. But when we are talking about 128 bits, we are talking about what we call undecillion IP addresses. I don't even know how to count that. Okay, but it's just to tell you that there's more than enough, Okay, and then IP version 6 has what they call improved packet handling, simplified header with fewer fields, and you're going to see it. All right, in the IP version 4, we have so many information in the header bit, but in the IP version 6, it has very few information. So IP version 6 also eliminates the need for NAT because NATing was brought in order to maximize the public IP address due to the limiting availability of the private IP address. So the IP version 6 now has it in abundance, so no need for that. Now, this is how the IP version 6 header field looks like. Okay, it is like a simplification or simplified simplified version of the IP version 4. In the IP version 6, version 4, there's so many detailed information in the header information. But you see, in the IP version 6, basically you have the source and destination IP address. Then you have the version, the traffic class, the flow label, the payload, which is like the size of the data, the next header, and the hop limit. Finish. That's all that is there. So several fields were removed to improve the performance. And they were removed from the IP version 4. Things that were removed like the flag that was in IP version 4, the fragment offset, the header checksums, they are all removed from the IP version 4. Okay. So the hop limit is like the TTL in the IP version 4. You know, we talked about the TTL, and that's like the hop limit in IP version 6. All right. Now, IP version 6 packet may also contain extension headers. All right, extension headers have actually provide optional network layer information, and they are actually optional and are placed between IPv6 header and the payload. And sometimes they may be used for fragmentation, security, mobility, support, and things like that. So unlike the IPv4, routers do not fragment IPv6. So how does a host route a particular packet? Now, a host does what we call the forwarding decision. Packets are always created at the source, and each host device creates their own routing table. So a host can send a packet, to itself, maybe like what we call the loopback. Now, where's that my command prompt? I don't know if you guys can still see it, but no, you cannot see it. Okay. All right, so I believe you should be able to see it now. So, for instance, every system has what we call the loopback address. The loopback address is the IP address, like a virtual IP address given by the operating system on the network interface card by default. So if I say IP config, you see, this is the IP address that my system has. You can see this is my current IP address, okay? But my system has, even if I am not connected to a network, even if I don't have an IP address, my system has an IP address of 127.0.0.1. That's the loopback interface for IPv4. So I can now decide to ping 127.0.0.1, and I ping. You see, I'm going to get a reply. All right. But what is this telling me? It's telling me whether I'm connected to a network or not. This IP address will always reply, and it will always reply because that is a loopback address. And each host device creates its own routing table to include itself, which is this. If it is an IPv6, this is the loopback address for it. All right. So every host has what they call the destination of its own LAN, and devices are not on the same LAN are called remote hosts. So I have a network which is sitting on a switch, and then I have PC1 and then PC2. They are all connecting using this particular public IP address. If for any reason that they want to talk amongst themselves, they can do so without the need of this router. But if they wish to reach out to maybe a system outside their local network, that is where they needed the issue of the router. And that router is the guy that will do the forwarding decision. Okay, that will do that particular decision. So the source device determines whether the destination is local or remote. How does it know? Because of the subnet mask. Now, a subnet mask, if you can see here, if I do my IP config, you can see that I have a subnet mask here. The subnet mask actually identifies the network portion of that particular network. And so any IP address that does not belong to that particular network is known as a remote device. Okay, so, and then it will give you the default gateway. The default gateway is trying to tell you this is the door you are to forward the traffic whenever you are going outside your local network. Okay, if you're going outside your local network, you go through the default gateway. And that's what we're talking about. So a default gateway is like the interface of the router that is at the border of that particular network. All right, it must have an IP address in the same range as the rest of the local area network. And even it can accept data from LAN and is capable of forwarding traffic off of the LAN. It can route to other network as well. So if a device has no default gateway or bad default gateway, its traffic will not be able to leave that particular local area network. So it's like you build a house. You build a house, and then inside this house, you have a door here. This is the door that you use to enter into the house. This is the door that you use to go out into the house. So you have people in this house, and they are inside this house, and inside this house is called a LAN. So far they are moving within the house, they are not going outside the house. They have no need for this door. This door is the default gateway. They have no need for it. But the moment they want to leave and go to visit a particular friend in another house, that is when they are going to exit this particular local area network and go to another network outside. And that's where the default gateway comes in. It provides the door that will take them outside. And then once they go outside, if they are done, if they want to come back inside, they go through that particular. So that is the job of the default gateway. All right. So the host will know the default gateway either statically or through a DHCP. So anytime you have an IP address, you have a system, you need to check the IP addresses that it gets. Among the IP addresses, if it's given by a DHCP server, there's always a default gateway. But if you are the one that is assigning the IP addresses to it, you will need to give it a static default gateway, because the default gateway now is the IP address of this interface here. So all the systems within this, if they are going out, they must follow this particular interface. And then anybody out on the internet, if he wants to come to this particular LAN, it must come through this particular interface, right? So how does your system record its own routing table? What is this routing table? It's just a table that says that anytime I'm going anywhere, this is the route to follow. Okay, this is the route to follow and things like that. Okay. All right, this is the route to follow. So if I come here, where is it? Come to my command prompt. All right. And I want to check my routing table. I just need to run the command netstart -r. All right. So let me clear this. Then I say netstart space -r. Okay. Now, having done this, you see, it has brought me my routing table of my laptop. Everybody's routing table is there. So you see, saying this is my IPv4 routing table. What is this IPv4 routing table? It's just a table to show all the places, anywhere I am going. This is the road I will follow. Okay, so you see, like this one is like a default gateway. Any destination with any subnet mask, follow this gateway. This is like a default route. Yeah. Default route. What is this gateway? This is the IP address of my own router, the router in my house. So if I do show IP config, you will see this as my default gateway. And then it will tell me the interface. That interface is my own IP address. So if I'm going to this destination, this is one of the IP addresses of the places, sites I'm visiting. This is my loopback address. So you see, it tells you the destination. If I'm going to any of this destination, all right, I will have to come and follow this particular interface or the particular gateway. So that is the routing table. And then for the IPv6 routing table, it also has its own active routes or the routing table. Okay, so the routing table is found also in the router, because that is what helps the router to be able to make its own decision, especially when it comes to routing and forwarding. Okay, so let's look at the concept of routing itself. A router basically does two things: path determination and packet forwarding. The act of path determination is based on the information available to the router. It can be able to predict and determine the best, safest, reliable path in order to forward the packet. Okay, that is what the router does. And the forwarding is the actual determining of which interface to use as is forwarding that particular information. So what happens actually when a router receives a frame from a host? Okay, this particular PC is sending a particular frame, and then this particular frame or this particular information has a destination address. You see, This is the destination address. So if this is my own destination address, that means I know where I'm going to. Once the packet comes to this particular router, this is router 1, the router now checks for its own routing table, whether it has any information about this destination. So this is the routing table for router 1. And in the routing table, the router says, I have an address to this destination, and you follow through this. I have an address to this destination, you follow through this interface. And then I have an address to this destination, 10.1.1.0, and you follow this interface. And then if there is any other destination that you have that I don't have inside my routing table, forward it out through this particular default route and then this interface. That is what is contained in this particular routing table. So what we can see here is that the packet now says that I have a match to this destination, 10.1.1.10. And where is it going to forward the packet to? It's going to forward it via router 2. And that is why you see from router 1, it will forward the packet to router 2. When router 2 now receives this particular information, router 2 will now carry out the same thing. It will now check its own routing table and ensure that it has the destination to it. And inside the routing table for router 2, you see that this particular network is found inside. And that is how the router will be connected. Now, inside the routing table, there are certain other kind of information that you tend to find there. There's what we call directly connected networks. When you say a network is directly connected, what we are saying is that there is a particular interface, a cable that is connected to it. That and the details is found in the routing table. Okay, so those routes are automatically added by the router, provided the interface is active and has its own addressing and things like that. That's where they say directly connected. You don't need to worry yourself by saying, let me add this particular route in the table, because it goes in there. Then you have what we call the remote routes. Remote routes are not directly connected. They are like routes that are not connected to the router at all. For instance, you see this is router 1 here. And then router 2 is connected to router 1. But observe, this remote network here, this one here, has nothing to do with router 1. So it is remote to router 1. So in that case, you will need to add, this particular network into the particular routing table. So these are the routes that the router does not have a direct connection to and may actually learn it either manually by imputing a static route or dynamically by using maybe a routing protocol or things like that. Okay. Then you have what we call a default route. A default route is a route to say, if you are going anywhere and your destination is not found in my routing table, just follow this door. Anywhere you are going in the world, so far your destination is not found, my right, just follow this one. That's the default route. Okay, that is how it works. Now, in the course of routing, we have two types of routing. We have what we call static routing, and we have what we call dynamic routing. Static routing is when the network administrator logs into the router and then impute the route that the router will use in making decision. So the network admin will say, okay, if you want to go to network A, follow this interface. You want to go to network B, follow this interface. Going to network C, follow this interface, and things like that. Okay, that is the aspect of the static routing. But the dynamic routing is saying that the network administrator does not actually need to come physically to impute the route. The router itself will learn it. All you need to do is configure a protocol that will help to do it. Okay, so static routing must be configured manually and must be adjusted manually by the administrator when there is a change, or when there are updates and errors or there are corrections and things like that. And then it is usually best for maybe small networks or non-redundant networks and stuff like that. But in some cases, it is also used in conjunction with a dynamic routing uh, protocol. Sometimes you use it to configure what we call a default route. So how then do you configure a route in the routing table? You have maybe this router one. You go to your global configuration mode and type the command IP route. Then if you type IP route, then you will now put in the IP address of the destination or the remote network. The IP address, then the subnet mask. After doing that, then the next thing is you put the IP address of the next hop router. You are pointing it to say, okay, if you're going to this destination, this is the vehicle to enter that is going to take you, right? Now, like we said, in the dynamic routing process, the router discovers and learns about this route on its own automatically. All right. And it maintains an up-to-date information. So if there is a change in any of the route, you don't need to come as an administrator to begin to correct, to update the routing table. No, the router will do so by itself. And it chooses the best path for the destination based on the information that it has learned. So those are like the two. Now, this is a typical example of what a routing table should look like or looks like. All right. To access the routing table, you need to use the command show IP route. Show IP route. And once you enter that command, you are given an information base. Okay. This information base tells you how to read the routing table. You see there is an L, there's a D, there's an N1, there's an E1, there's an I, there's an IA, OA plus, and things like that. Now, what do they all mean? When you see an L, it means that it's a directly connected local interface IP address. That is where you see some things, this one, this L here. See, that means this interface is directly connected. 192.168.10.1. So let's look at it. Look at it here. 192.168.10.1. That's what it means. It's directly connected via the cable. All right. When you see C is a directly connected network also. Okay. So you see, but this time around, it gives you the network address 10.192.168.10.0, which is this network address. You see it here. Then S means that that route was configured statically by the administrator, manually. That's where you see this one. In fact, when you see the one that has asterisks, it means that it's a default route. So you see this route was created by the network administrator itself. When you see O, it means OSPF is a dynamic routing protocol. When you see D, it's also a dynamic routing protocol, means EIGRP. How do you know all these things? They are all found in the information table above there. So that is like the brief of what we have in module 8, which is network layer. So since we have a small amount of time, we will go into module 9, which is also brief, which is address resolution protocol. Okay. So in the meantime, I will enable your attendance so that you will be signing it, and while we continue with that. Okay. Okay. I see somebody has a hand. Someone has a question. Ojo, Lufemi, do you have a question?
Thank you very much, sir. I just quickly want to ask. In literature, there are some other routing protocols like RIP version 1 and 2. They are not featured in the routing table you just showed us. Then also I want to ask, does a router build its routing table the same way switches build their MAC address table?
Okay. Very good question. I see multiple hands. So maybe what we'll do, we'll enable the attendance and then we will just answer the questions and then we'll call it a day. All right.
Okay.
I have enabled the attendance. Now, let me get to your question. Number one, routers build their routing table in two ways. One, manually or dynamically. When I say manually, it simply means that the network administrator is the one that will manually create the content of the routing table. When we say dynamically, there are dynamic routing protocols. We are yet to talk about them. We'll talk about them in much later class, okay? We'll talk about these dynamic routing protocols that once you configure on your router, then that protocol will be the one that will learn new routes and populate it into your routing table. So that is how the router builds its routing table, okay? Now, whether you see RIP or you have not seen other routing protocols there. What I've just shown you is just a sample, okay? It's a sample. We have other routing protocols. So when you come to do your configuration, you're going to see the other routing protocols that are there. All right, thank you, Ojo. The next person is Dr. Osho Sivin. Can you increase your volume, please?
Okay, good evening, sir. Are you hearing me now?
Yes, I'm hearing you.
Sir, I want you, how does the system calculate the time that to leave? And why is it that all the systems in a network always have the same time to leave? I
Hey,
don't know whether you get my question.
okay.
You get my question?
Yes. You say, how does a system calculate time to live, right?
Yeah. And why all the nodes in a network have the same time to leave?
Okay. Now, first of all, not all the systems on the network have the same time to live. They have a similar time to live, which means they may have it looking like the same, but there are instances that makes it change. Okay. If within your own network, you are testing connectivity to a particular destination, all of them are going to have the same time to live because you are having the same destination. But you can try a destination, two different destinations, and see what happens. We're going to practicalize that now and see. Now, the time to live is in networking actually determines, like we said, the lifetime or the hop that the data packet can travel before being discarded. So this time to live value is used to actually prevent infinite loop because the packet keeps going and coming and going and coming. So it's used to prevent infinite loop. So when a packet is generated by a source device, the TTL, which is the time to live, is set to an initial value. That initial value is the one that you say most systems have. It's like saying anybody that is going from Lagos to Abuja, I'm going to give him 100,000 naira. That's like the initial value. Depending on what you're going to spend on the road is up to you. But at the point of taking, you have 100,000 naira to leave from Lagos to Abuja. Okay, so this initial value is typically configured by the operating system or actually the network application itself. Sometimes you see it like 64, which is used in Linux-based system, or 128, which is used in Windows operating system. Sometimes 255 is actually the maximum value that can be set. But the important thing is that the TTL value decrements to 0 each time it passes through a hop or it passes through a router. It decrements by 1. You understand? So if it passes through so many routers, it keeps decrementing or decreasing and things like that. That is how it actually does it. So let me see if I can, where is that my command prompt? Now, if I run a ping to google.com, all right, you see I have a TTL of 53. If I run a ping to cisco.com, now, can you see the TTL value has changed? I'm having 40 here and I'm having 50. Can you mute yourself, please? All right. So if I now ping, let's say, CNN.com, look at the TTL value has changed from 40 to 48. So the TTL value is not like is a constant value for all. No, it just gives you the value based on the destination that you want to take. I hope it has been informative enough for you. Okay?
No. Yes. Thank you.
You're welcome. The next person is Obisenya Olasupo Isaiah. You can unmute yourself and ask your question. Okay. Maybe he's not ready to ask the question. All right. So I see this is all the hands that we have. These are all the questions that we have.
Good evening. Good evening.
Good evening.
Please, I want to ask. We are in module 9 now. Are we going to do our assignment up to module 9?
Okay, that's what I want to address now. Okay.
Okay, sir. Okay.
Now, if you recall, if you check your portal, you have different checkpoint exams. All right.
Yes.
Now, the checkpoint exams that I have activated, by now you should have been done with the second checkpoint, the first checkpoint exam and the second checkpoint exam. So the first checkpoint exam is done and is locked now. So those who have not done it, maybe have to miss that. But for those who have not done their second checkpoint exam, who have not